right. Well, thanks everybody for sticking around to the last talk of the day. So is that good with the mic? Everybody can hear me? Okay, sounds good. All right, so yeah, I'm from the University of British Columbia, a couple hours north of here by plane, so not quite home, but nice to see the Julia community showing up on the West Coast. So yeah, I'm going to talk today about this package that my research group at UBC, so I'm a PhD student at UBC. I'm going to talk about this package called jInv that our research group's been developing at UBC over the last few years for it's a kind of a framework and a set of tools for solving partial differential equation constrained parameter estimation problems. So we're going to talk a bit about that from the domain science point of view, how you can use this package for your own problems, and also kind of more from the software side, talk about how it's been kind of why we decided to go about writing this package the way that we did. To give a little bit of context, so our group is mostly interested in kind of these inverse problems in imaging, mostly motivated by problems coming from geophysical imaging and also medical imaging. So in these sorts of problems, generally what we're trying to do is estimate the kind of the spatial structure of the physical properties of some object that we're interested in. So for example, in the geophysical context, we might be interested in kind of in estimating how the electrical conductivity or the density of the subsurface of the Earth varies, kind of doing that based on measurements that you make either kind of from the air or just at the surface of the Earth, so essentially remote measurements. And so kind of mathematically, how we represent that problem is as an optimization problem, kind of relatively straightforward in structure, but not so much computationally. So we collect our data out in the field, which we call D, and then if we have kind of a guess at whatever our model of, say, the subsurface in the geophysics context is, then we can generate kind of a synthetic data that goes with that model, and we just solve an optimization problem that tries to minimize, in some sense, the discrepancy between our kind of our measured data or that we get from the field and the model data that we can kind of computationally generate. And that's a very ill-posed problem in most cases. So we add kind of a regularization term to that, which I won't really go into at all here. And I mean, so essentially that's kind of, in a way you can look at it as just a regularized nonlinear regression problem. The trick is that every time we want to kind of evaluate our objective function for a given model, we have to solve at the very least one partial differential equation, and normally in a kind of production scale problem, tens of thousands of them potentially. So it's a computationally intensive procedure. And then if we want to kind of write a computer problem to solve these sorts of problems, we there's a lot of parts from kind of ingredients from different areas of scientific computing that go into that. So obviously we need optimization, numerical optimization tools. We need methods for numerically solving partial differential equations. And one fundamental thing that cuts across both of those is solving very large sparse systems of linear equations. So, and the other thing is there's a lot of problems that kind of fall into this general form. And much like Oscar mentioned before, kind of we want to, if we have a new problem that's quite similar, we want to solve that by kind of putting modular building blocks together, which from a software engineering point of view, kind of talking to people at this conference seems pretty obvious, but I guess also like in Oscar's case, if you're here a couple talks ago, certainly in the geophysics community where I come from, that's not at all the norm. And then the next question is, if we want this kind of modular framework to kind of quickly get up and running to solve a new kind of PDE constrained parameter estimation problem, kind of what's the best way to go about that? So yeah, do we want to look at the Julia community, take kind of tools from the separate areas of sort of PDE discretization, the optimization community, and kind of interface those together? Or maybe look at some lower level tools, like for example, PETSI or Trilinos. And I must say, I want to be definitely really fair to the Julia optimization and the differential equations communities. I think we did a lot of our stuff from scratch, which was partly because we started this a few years ago when those tools were a lot less developed than they are now. And we should maybe look again at kind of stopping doing some things ourselves. And again, we want to work at a higher level of abstraction than say, directly calling tools from, say, Trilinos that are all C++. And there are some other packages similar to this coming out of the geophysics community, but they don't really have the kind of the HPC ready characteristics to really apply it to production scale problems. And the other thing is we really want to kind of shorten the kind of pipeline between research code that grad students and academics write and code that we can use in production. So I work in an academic setting, but our group works very closely with industrial partners. And kind of traditionally, the way our group has worked over the last kind of 15, 20 years, is grad students write research codes in MATLAB, and then they hand them off to a lone Fortran programmer who writes production codes. And we really we want to move away from that. We want to be able to take our research codes and with kind of minimal modification, get them ready to run at scale on industrial problems. So Julia provides a great setting for doing that. So that brings us to our package, jInv, which is short for Julia Inversion. And so it's has a collection of optimization routines, building blocks for quickly creating PDE discretizations, and kind of interfaces to tools you need like sparse linear solvers. And if you're interested in this stuff at all, check us out on GitHub, github.com/JuliaInv. So looking at that forward problem, of course, really the hardest part of that is solving a lot of PDEs in parallel to kind of really evaluate the objective function in our optimizations. So in our group, our bread and butter is finite volume methods on these meshes that we call octree meshes, which are essentially locally refined rectilinear meshes. We're also dabbling with finite elements on tetrahedral unstructured grids. Right now, we just do, for those who are finite element people, we do first order Nedelec elements, and that's it. But yeah, and we have interfaces to Krylov methods for linear systems and Mumps and Paradiso, which kind of we consider the best of breed for sparse direct methods. So just running out of time here, but just to kind of very quickly look at a code. So one example here, we have what we call controlled source electromagnetic systems, where we have a kind of some source of electromagnetic waves that gets towed behind a ship, and then we kind of measure the electric fields that come from that transmitter interacting with the subsurface of the Earth, and then that's governed by the PDE we have up here, and the highlighted element is a coefficient in the PDE that represents our kind of the electrical conductivity structure in the subsurface. So if we want to discretize that PDE, this basically does it here in Julia in a way that's completely mesh independent. So we can have this same code that gives us a discretization of that differential equation that can apply on a regular mesh, on an octree mesh, on a tetrahedral grid. Basically just by calling these kind of generic functions, this give us differential operators, and calling them just using multiple dispatch on the type of mesh object that we pass. Because I don't have much time, I won't actually go through it in detail. And just very quickly to return to the optimization problem that we're trying to solve. The sum term here is very important. So we have to solve a lot of PDEs, and we have a system for doing that basically automatically, where we construct, just about finished it, where we construct our kind of representations of these discretizations of the PDEs remotely on various workers, and then to our optimization routines, we feed it a vector of these remote references to our forward problems that we store in Julia in these remote channel objects, and then we can kind of use these forward problems on the remote workers as we need them, take them out of the channel, modify them, put them back in, and save that data on the remote workers for later. And so basically out of time. If you're interested, take a look at some of our tutorials, Jupyter notebooks, to kind of get you up and running. And thanks to the community for helping us out and all the contributors, and thanks for listening.